The other day, my kid came to me and asked me a question. Hey dad, which planet in our solar system has the most number of moons? And I straight away said it's Jupiter with around 88 to 90 moons. Now, you take a step back and try to understand what was the problem with that statement. Well, there are many, but the most dangerous is that it's a wrong information. As of today, the planet with most number of moons is actually Saturn. Now, was I trying to give this answer intentionally wrong? Of course not. Because Jupiter, in fact, was the planet with highest number of moons certain time back when I learned about it. So if I kind of look at this again, the problem is that I just gave that answer top of my head with the memory that I had for this question, right? There was no source. When did I learn it? I still don't remember when did I learn it. The second is that it is out of date. If I had done my research, let's say I did some Google search or something like that, I would have probably figured out that the right answer is Saturn, right? With around 146 or maybe more than that, I don't know. But I know that I would have probably known that the planet with most number of moons is Saturn. So that's the same analogy with LLMs, right? And this is a kind of hallucination, right? It's hallucination based on the data that it had. It's not probably on the prediction. But in this video, what we're going to learn is that what are those types of hallucinations and how do we create this knowledge boundary around LLMs with some updated information at the top of the data that they were trained on, so that we reduce these hallucinations. What is that exact process? We try to figure that out. So let's get started with this video. So let's start with hallucinations, right? Now, by definition, as in the previous videos, I've been talking that these models are supposed to be creative, right? By design, because their job is to give you creative answers. So when you go to something like a Midjourney or ChatGPT today, and you ask a question that, hey, can you generate an image where a cat is wearing formal clothes? It has to imagine that how a cat would have looked like, because cats generally don't wear formal clothes, generally. At least not in India, what I've seen, maybe outside. But to create an image, to basically picture that image, it has to be creative enough based on the data on which it is trained. Now, what happens to us when we try to imagine things? We try to imagine things that don't exist today, right? In a sense, we also hallucinate. But this hallucination, the way we are using LLMs or other generative AI models for our value-added services in organizations today, we have to make sure that we have a controlled hallucinations. We give them the freedom to hallucinate as much as possible in certain cases, but in certain cases where we need factual answers, we have to control that. So let's look at what are the 4 major types of hallucinations. Number 1 is obviously factual errors, right? When you ask a question which is the capital of India and it says Mumbai, that's a factual error, right? And this is the most dangerous type of hallucination because this has to be controlled. This is where LLM goes absolutely wrong. The second hallucination is called sentence contradiction. Now, what is sentence contradiction? Is basically you get to see this in smaller models, not in larger models today. But for example, it contradicts itself, right? While you are having a conversation with the LLM through a chat application, one time it says that, hey, the color of sky is blue. After some time it says color of sky is red, right? It contradicts itself, its own sentences. The third type of hallucination is called prompt contradiction. I ask it to do something and it does absolute opposite to this. Again, you do see this in smaller models, smaller language models. But one example could be write a positive review for my organization and it writes an absolute negative review, right? And the fourth and the final type of hallucination I want you to concentrate on is called nonsensical outputs. Now, this is the least dangerous type of hallucination, but in some cases, I'll give you an example where I personally face this. But this this kind of gives you extra information that you have not asked for. For example, you ask a question: who is the what is the capital of France? And it says the capital of France is Paris. By the way, Paris is also the name of a singer. Now, I have not asked it to give this answer. Now, in my experience, we created a chatbot in our organization, right? And it's for one of the group of functions where the to the point answer mattered a lot for that function, right? But when they asked this question to the chatbot, it gave the right answer, but it's pretty longish, right? It's not exactly to the point. And this type of hallucinations we can control through controlling our system prompts, right? It's not giving you anything that you have not asked, or it is not giving you anything that is not correct, but it's giving you something that you have not asked, right? And as I said, it can be controlled over system prompts. So if you tweak the system prompts, it will get fixed. Now, with that understanding, let's concentrate on factual error and how do we fix this, and how do we create this knowledge boundary with updated information. So let's look at why LLMs give this factual error or plausible nonsense. And for that, let's get back to the question of a planet with most number of moons. So there are three main things that has happened, right? So it was trained on unfiltered internet data, which was pretty big. There sometimes can be biased, right? For example, let's say if you go to Reddit or if you go to any Google reviews for one of your Amazon product that you are trying to buy, and you just look at those reviews, do you trust all of those? Maybe not, right? So you will trust a review when you see someone has posted a video of something that is working or not working, which gives you more confidence. But when these models are trained, there are a lot of huge number of data that was taken, which can be biased towards one another, right? The second point is that LLM by default as a model doesn't have this lookup ability, right? It cannot just go ahead and search at a given point of time. That is the engineering that needs to be built around it. And the third is the knowledge cutoff, right? Let's say if I take my example, if I am the LLM, right? So my knowledge cutoff was probably 1990s or 1992s, right? And I knew that Jupiter was the planet with highest number of moons, which is the case for LLMs also. Right now, the LLMs are trained more frequently with data, but it is still the just-in-time of a data, right? So, for example, if I just take an LLM today and say that, hey, tell me your details about the event that happened yesterday, and it doesn't have the lookup ability as we saw the previous problem, it will give its own information with the best that it knows of, right? So that is one of the reasons, one of the three of the reasons why you see this plausible nonsense or hallucinations. What is the solution then? The solution is creation of a knowledge boundary and the technique we call retrieval augmented generation. So if you look at the same question right now and imagine a scenario like this, that what planet has the most moons? If there is a way I can say that, hey LLM, first you go and look it up, right? I have some documents storage for you, or I have given you this capability of doing Google search. It would have probably found out that, okay, one of the NASA's recent document or the PDFs that I gave to it from where it can actually search the answer, which are NASA's documents, it would have found out that Saturn has the most number of moons, right? And then it would have given me the answer that, hey, here is a source where I found it, and according to this source, the Saturn is your answer. So what happened in this case? I have two things. One is I have citations, right? So I get to see when it gives me the answer from where it is trying to find that out, right? And the third thing is that the second thing is that we get to see a more accurate answer because it is actually trying to get the answer from an updated information. So what is retrieval augmented generation? The retrieval part is actually fetching up-to-date information from an external knowledge base. This knowledge base can be created by you in terms of a database store, and we'll discuss about that pretty soon. Um, or it can be something like giving engineering capability of doing a web search to fetch latest information. The A, or the augmented, stands for enhancing user's original prompt or the question. Like, I asked a question, it knew that I have the answer, but then it went ahead and saw some knowledge base to get the updated information, and then relook at the answer to relook at the question that was asked by the user to augment it again with more factual context. And the third is generating. So now that it has all the information, it has retrieved all the information, can it generate the answer the way user wants to look at? Like, for example, I would have asked that what planet has the most number of moons, give me the answer is one in one word, then it has to generate the answer that way, right? So that is the retrieval augmented generation, which basically kind of helps us create that knowledge base. Now, before we begin looking at uh, 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 how actually LLM sees information, right? We need to understand two concepts. One is a vector embedding or embeddings, and the second is a vector store, right? So let's get started with what are embeddings. So before we look at the entire RAG pipeline, that's very interesting, we'll do that. But we'll try to understand a concept called embeddings. How do we store the data for LLMs, right? And to know that, let's take unstructured data, because this is where things get a little bit interesting, because unstructured data meaning a text in a PDF, sound, image, etc., right? So let's take image, right? So when we take image, let's say you have two images, like one is sunset in a mountain and sunset in a beach. Now you have two pictures and you need a system where you want to retrieve these pictures. Now one way is that there is a keyword search, which we actually do. So we store these images and then we try to tag these images, right? So for example, the first image we'll tag it as sunset, mountain, or something like that. On the other hand, we will say that sunset, then probably beach, sea, etc. Now, what is the challenge here? The challenge is that when we try to retrieve images where we say that images with warm color palettes and no urban elements, this is where there is a gap in the previous process, and we call it semantic gap, right? And introduced a new technique called semantic search through embeddings, right? And if I try to bring the context of text here, how does a computer understand that when I mean that, hey, fetch me the data for quarterly sales, it is semantically related to something like a revenue growth, right? And this is where we introduce something called vector embeddings, where we convert the text and images into a list of numbers or a vector, right? And we try to capture or fill this semantic gap, capturing the semantic essence of data, right? And let's look at the example of this once more. So how a vector embedding model. So before that, I think you can convert the data into vector embeddings using a lot of embedding models that are available from OpenAI. They are available from Meta. They are available from Gemini as well. These are low-cost models which can just take the data and convert into vector embeddings. Now, if I take the first picture, when it convert, what do you mean? What do I mean when I say that it converts the data into numbers? Is that in the picture of mountain, right, sunset, it might have different weightage for different aspects of this image. For example, there are high elevations, so it will have a higher number for that part, right? So it has like mountain and on higher elevation. there are low urban elements here because we're at the mountains, we're the hills, and etc. And for strong and warm colors, it will have a higher number, like your etc. Similarly, when it takes the beach image, your low urban elements and strong warm colors will be somewhat similar to the previous image. But when it comes to elevation, the elevation number will be lower, right? So when I ask a question that, hey, I need mountains, sunset in a mountain, it tries to retrieve looking at this number, and it tries to do something called similarity search, where it tries to understand the approximate nearest neighbor of what is asked. So for example, it tries to figure out what are low elevation numbers that I have around the question that was asked, right? If I ask this question. So for example, it tries to figure out what is 0.13, 14, 15, and then it tries to, because I asked for sunset, it tries to understand that, okay, from the sunset, what are nearest to my question from the numbers perspective, and it tries to collate all this information and present me a picture which is very, very closer to what the answer that I'm looking for, right? And it feels that I'm asking a natural language question to fetch some information. Now, if you understood this question, this point, that it actually tries to retrieve from the information or the embeddings, it actually has to convert my question also into embeddings, right? To understand that approximate nearest neighbor, or the ANN that I was talking about. So the moment I ask a question, give me picture of a sunset in a mountain, it will look at my question and it will also divide my question into vector embeddings, and then it will do a similarity search trying to find out that ANN, right? Second thing is that once we combine these numbers, when we create these numbers, vector embeddings, right, we have to store that, and we cannot store them into a traditional relational database, right? And this is where comes the vector database. Now, what are vector database? So vector database is a specialized database designed for a quick search on billions and billions of vector embeddings. So you can imagine, so instead of having like 10-15 tags in the keyword search that we were talking about, here it has to analyze the image and create many embeddings or numbers to justify that image, right? So it is a database which can contain that scale of information in terms of numbers. The core function is, it's obviously very, very fast because it is similarity search. Now it concentrates on the question, right? So as I was saying, it looks at my question, it converts my question into vector, and does this nearest neighbor search, or the absolute approximate nearest neighbor search that I was talking about, and it does it almost instantly, right? And the engine behind these databases is ANN, or the approximate nearest neighbor. So if I try to put everything into a RAG pipeline right now, so how does this pipeline look like? So what was our company's revenue growth last year? Let's say this is the question that was asked, right? Now this question is converted to embeddings to create that bunch of numbers, right? And then if you see in this picture, the query vector that gets created based on my question is used for the similarity search to find out the nearest neighbor, or the approximate nearest neighbor from the vector DB. That circle of dots that you see, it's that vector embeddings. And imagine that this is actually thrown to the vector DB to find out, okay, what is the nearest number that you find for each of these vector array, right? And then it gives a set of chunks of numbers, vector details, which according to the similarity search should contain the answer to the original question, right? And these chunks are given to the augmented engine, which basically uses the user query and the retrieve chunk to kind of reimagine the answer from that given knowledge base. Then the LLM kind of tries to generate the relevant answer from that chunk, right? Which is more grounded, because the fact that it gets the chunks in the step in the middle, as you see, I can actually create my own citations around that, right? So I can say that I'm giving you this answer because of the data available in this space, or in this page of a PDF, right? Or in this timestamp of a video, right? I can annotate those things so that user is more and more confident that the LLM is not hallucinating, and LLM is only used to basically generate the answer the way we want to look at that answer, right? So at the end, you get a grounded answer. So this is the entire RAG pipeline, and that is the retrieval augmented generation. But there are some problems around retrieval augmented generation as well, and let's discuss on that. So in RAG, if you have figured out, most of the time, if you have used RAG-based chatbots as of now, you sometimes feel that when your knowledge base is bigger, like more than like millions of PDFs or something like that, if your chunking strategy is not that great, you are not actually getting the right answer from that knowledge base. And why this is happening? Because an answer from RAG is solely dependent on the retrieval capability, right? So if it is not retrieving the right chunks, then it is actually going to fail and give you wrong answers. So for smaller but not so smaller in today's time, there is another concept called CAG, right? So let's look at what is CAG, or Cache Augmented Generation, and when do we use RAG, or when do we use CAG, or when do we use hybrid? Let's try to find that out right now. Now CAG, because like 2-3 years back when these language models were released, their context window, what is context window? How much information at a given point of time it can hold. So RAG is a place where it can hold enormous amount of data, and using retrieval strategies, we retrieve that data when a question is asked. CAG, on the other hand, is basically a context window of how much it can retain at a given stage. So can I give it a 1-page PDF and ask a question on that directly without doing the RAG? This is where the context window of the LLMs kind of comes in. Now 2-3 years back, context windows used to be very small. Like I think for the first time when GPT was released, it was 4096 tokens, and again the tokens around 1000 words equal to 750 tokens, or the reverse of that. Today we have models which has context windows of 1 million and 2 millions in models, right? That gives us the feasibility to try an alternate strategy, which is Cache Augmented Generation, or CAG. So when I say 1 million context or 2 million context, it can actually contain, it may not contain like millions and millions of data, but it can contain pretty large amount of data, right? So for example, an entire Harry Potter book set, it can contain at one given point of time, right? So instead of retrieving on demand, which is retrieving on the word, I'm pushing a little bit more on the word retrieving, because if retrieving fails, my RAG will also fail. We try to preload the entire knowledge base into the model's context window, because the model can hold that much of context window. If I try to give you an analogy between context window and the knowledge base, RAG knowledge base, imagine that, let's say you have done a BTech or BSc or BCom, you have done 3 years of study. Whatever you have learned there, you cannot remember at everything together, right? So when you face a problem, let's say you are a student of computer science and you face a problem today and you try to remember, okay, let me go back to my knowledge base and figure out, did I study anything around that? And then you try to retrieve that information, right? But imagine if you have a superpower today where you can actually remember everything that you learned at any given point of time. That is the context window analogy of LLM as well, right? So the model memorizes all documents in the single pass itself. I can give it like all the 7 or 8 books of Harry Potter and it will remember. And now when I ask a question, imagine that there is an open book in front of it. It can just quickly go and find it out instead of relying on a vector database where the vector embeddings were stored, right? So the core difference between RAG and CAG is that RAG fetches what it needs and CAG loads everything up front, right? Uh, so I think there are certain cases where you will try to use CAG or RAG. So I thought of basically try to figure some use cases for you. But before that, if you are an architect and you have to choose between RAG and CAG, what are your choices? And if I have the matrix of accuracy here, your RAG is probably the winner, because there is a retrieval happening, of course. If I have, given that I have done my retrieval strategy right, there are millions and millions of information that I can query, right? On the other hand, I have to, for CAG, I have to depend on its context window. And if its context window is 1 million, and if I have a knowledge base that is going beyond 1 million, even 1 million one, that one is getting cut, and I might not even know about it. If it comes to latency, because there is no similarity search happening, similarity search is fast, but CAG is faster, the lower latency, because everything is in your memory. Imagine the first question that I asked, my kid asked me that, which is the second, my answer was very instant, right? Because I tried to understood from my memory. Now the problem was that my memory was wrong, but here imagine that it can hold the entire knowledge base into the memory at any given point of time. So for latency, the winner is CAG. When it comes to scalability, obviously millions and millions of documents, there is no comparison with CAG. So your RAG is the winner. It can hold any number of, your vector database can hold any number of information in their knowledge base. And when it comes to data freshness, it's again RAG, because you have to provide the new information into a CAG's memory window, or in case of CAG, for a LLM's memory window every time. Whereas you can just keep on ingesting information into the RAG or the vector database through an engine, and LLMs will use that data at any given point of time, right? So these are the four metrics on which you can choose RAG or CAG. But here are few things where you can use, you can probably use RAG or CAG or certain things. So let's look at one by one. So scenario one, IT help desk bot. So build a bot to answer questions using a single 200-page product manual. What do you think is the answer? Pause it. I'll give you the answer in a moment. But if you want, you can just pause it and try to think from whatever we have discussed till now. Scenario 2 is a legal research assistant. Build a tool for law firms to search thousands of legal cases. And this can be from many legal documents. It can be from legal websites where the information is stored, or proprietary legal documents as well, right? The scenario 3 is clinical decision support. Build a system for doctors to query patient records, treatment guides, and drug interactions using consultations. So you can pause for a minute and give it a thought. Okay, so hoping that you have actually paused the video and tried to come up with the answer, let's look at what is the correct answer. So the scenario 1, obviously CAG is the situation. You just have a 200 page. It can hold up to thousands of pages. So 200 pages is very small. And also you can have multiple PDF. You don't have to have the entire thing into one PDF. You can have multiple PDFs totaling up to like 1,000 pages or 2,000 pages or something. For some LLMs, it's close to 3,000 pages. For the second case, it's RAG, because your information is huge. It's big, and you have to basically hold it inside a vector database and fetch it on demand. And the third is clinical decision support. It's basically your hybrid approach, because sometimes you need to use RAG when you have to retrieve relevant subset of data for a specific patient history. Then use CAG to load retrieved context into the memory so fast. So for example, let's say you want to have the patient history, you retrieve that, but patient might have a lot of reports that he or she is having, which was done today. You can fetch those reports at a given point of time because your context window is higher, right? So I hope you understood the difference between RAG and CAG. And before we end the video, there is one last concept that I want to talk to you about, which is the types of RAG that you can do. There are 25 different types of RAG. You can go to archive.org and you can look at all the researches, right? But I hope it gave you the fundamental concept of RAG. But I want to peek into one of those techniques called GraphRAG, right? So let's look at what is GraphRAG and how it is beneficial. So in RAG, RAG is probably amazing when there is a Q&A happening between between the user and the system. Like for example, I ask a question that which planet has more number of moons, and it tries to look at information and gives me the right answer. But you can try this out if you have a RAG chatbot that you have access to. If you try to ask for a summary of the document, right, or summary of a document, then it might not give you this summary, right? And one reason why, I'll pause for a second to understand if you can figure that out. Because every time when RAG is happening, it is trying to do a search based on what you have asked. And what is your question here? Give me a summary. Now, to find that ANN, approximate nearest neighbor, it is looking at the word of your questions, right? It has converted that to also embeddings. Now imagine how there might not be any word called summary into your document. It's a semantic ask again that the user have asked, right? And this is where I think RAG will not fail. It will give you something, but it may not be entirely correct. But at a given point of time, it doesn't get to see the entire knowledge base together. And this is where we have GraphRAG, where basically retrieving information to understand relationship. So what GraphRAG does, which is the primary difference between traditional RAG and GraphRAG, is that it tries to extract entities and relationships between words as well, right? Apart from creation of the chunks, right? So it does not just create text chunks, it creates relationship, which can be people, which can be organization, which can be concepts, and maps that relationship together, right? So let's look at an example how GraphRAG can be useful, right? So let's say an immunologist has discussed virus response strategies with the CEO of a healthcare company, right? So when GraphRAG comes in, there are multiple aspects that we have to keep in mind when we try to get some insights of this conversation that happened between these two people, right? So an immunologist is specialized in medical research. A CEO is specialized in leadership, probably for a healthcare company, right? That he or she has. So a traditional RAG might find isolated facts about immunologists or CEOs. But a GraphRAG identifies through this entity relationship that happens that immunologists and CEOs have different entities attached to them. So it goes further than RAG to understand the nature of their conversation or relationship and what insights it can get. The immunologist has a direct and strong connection to medical research, as you can see in the picture, right? The CEO has direct connection with leadership and healthcare company or maybe other companies that he or she has worked on. The system then can quantify the strength of these connections to create more weighted graph that reveals a lot more insightful information just beyond the question and answer, right? So we are actually trying to and it sometimes it looks more like reasoning, because the LLMs are trying to analyze these connections before it actually fetches information for you based on the questions that you have asked. So now coming back to our architect's blueprint, we have seen RAG, we have seen CAG. Now the question that probably comes to your mind right now is that, hey, I can do that with CAG as well. So CAG is also not creating, it is actually looking at everything, and it should be able to give me the summary of the conversation that happens because it is getting to see. And you are absolutely right, it will. But what if the conversation is 7 hours, 8 hours, and the transcript can go beyond 3000 pages, or it can hold, right? So again, you have to take a decision. So let's relook at the blueprint again. So we understood we use RAG when your knowledge source is very large and frequently updated. You need citations and scalability. You use CAG, when you know the context window of the LLM can hold the information at a given point of time through the context window length. And you use GraphRAG when the relationship between pieces of information are as important as the information itself. Like you also need to rely on, in the previous example that we had, you also need to understand that who has the discussion, who had the discussion. Because you know that when an immunologist and a CEO is discussing, because of their natures, of their experiences, or their SMEs for different things, there might be some added insights at the top of it that we can bring into our information, right? So that is all about the information that I wanted to give you in this video, and I hope it gave you a good overview or the foundational understanding of this technique of RAG, the CAG, and the GraphRAG, etc. I'll strongly recommend that you go to archive.org and basically now try to find out what are the different researches that are happening on RAG, because you cannot stick to one strategy for your RAG, even for RAG, not CAG or GraphRAG. Based on your knowledge base, based on your business scenario, you might have to adapt different types of RAG scenario. In our organization, we have 7 different types of RAGs that we have done for 7 different scenarios. So I'll strongly recommend that you go to archive.org and try to search for different RAG techniques and strategies. Thank you so much, and I'll see you in the next video as well.